whether someone has pneumonia or not based on an X-ray scan of the lungs. That is where you may need a fair amount of computer vision and deep learning experience. But if you're working in another company where it's not really working with image-based data, they will still have some level of text data. And that's where a lot of useful data is in the form of text across most kind of companies out there, be it from a banking domain, be it from a logistics domain, so on and so forth. And that is where the data could be public, which is also known as alternate data, where you are either scraping the web or accessing data from data feeds, RSS feeds, APIs, or it could be private or proprietary data, where you are basically dealing with the company specific data. And hybrid data could be, again, public surveys, private surveys, so on and so forth. So this is where a lot of the useful data is in the form of text, and that is where you should have the motivation to at least know some level of natural language processing to be able to leverage these skills no matter where you go. So that is where this should give you some level of motivation as to, let's say if this was 3 to 4 years back, maybe NLP was seen more as a specialized field. But nowadays, let's say if you want to consider a serious career in data science, I believe this is something which you should know to an extent. Now, coming to the practical perspective of NLP models, most NLP models are basically realistic and affordable. What that means is thanks to open source technologies out there and open source frameworks, so on and so forth. Most of these NLP models nowadays are easy and affordable. You don't need to like shell out thousands of bucks just to build an NLP model or purchase some kind of a premium service to build these models. There are a lot of frameworks out there, be it Spacey, NLTK, TensorFlow, PyTorch, so on and so forth, where you can leverage the whole power of the open source community and these packages and build models which are understandable, which are realistic, and which don't cost you that much thanks to the power of open source. And you also have frameworks like Flask or TensorFlow serving, so on and so forth, where you can even deploy these NLP models. And thanks to the power of cloud computing, GPUs, cheap space, and so on, nowadays you can deploy these NLP models, even if, let's say, you're a small business or you're just one individual. You don't have to be like a Google or a Facebook to be able to deploy an NLP model also realistically. Now let's talk about some of the popular ways in which natural language processing is being used on a day in and a day out basis. So this is a very common slide which you'll find on the web with regard to some of the top applications of natural language processing. Let's look at some of these step by step, and then we'll do a deep dive shortly. So information retrieval is all about extracting the right kind of information, the most relevant information based on some kind of a search string or a search query which the user is entering. And the most common example of this is something which you folks use day in and day out, like let's say Google search, where you will be typing in your query in the search box, if you think about it, and click on search or press enter, and you will see the relevant documents or web pages being shown to you which are in line with the query you've typed in. So what's going on behind the scenes is information retrieval, where each query which you enter, that text string, is being converted into some kind of a numeric representation, which we'll talk about when we discuss about the text representation aspect of things, because you need to be able to represent text data in some kind of a numeric encoding format, which we'll talk about in more detail later. But the perspective here is that you need to convert this search string into some numeric information. And what happens is it tries to find out which are the already stored web pages, or which are the already stored documents whose text content is very similar to the search query which I entered. So that is where it will do some kind of a ranking, a similarity, a relevance sorting, and then it will show you the top relevant results. And this is where information retrieval is the field which deals with all of this. And I guess sentiment analysis is something we all are almost aware about, or kind of familiar with, where the idea is to look at survey data or feedback data or review data, look at the text content and say whether the customer or the employee is exhibiting a positive emotion, a negative emotion, try to find out the reasoning behind that, so on and so forth. Information extraction is all about extracting some level of structured information from this unstructured text documents. That is where we try to find out, okay, what are the key entities in my documents? What is the actors? How are they related to each other? What is the subject, the object, the verb, let's say? What object is entailed by what has happened previously? Those kind of aspects. And that is where things like named entity recognition, dependency parsing, constituency parsing with regard to grammar, these kind of things become useful. And a simple example could be looking at, let's say, invoices or even financial records, where instead of you going through pages and pages of a contract, so on and so forth, you can leverage some of these techniques like named entity recognition and so on to extract the key entities automatically for some further post processing. So that is where information extraction becomes handy, to extract the key information or the key essence or the key entities from huge documents. Language translation or machine translation is where you kind of try to translate from one language to another language. I'm pretty sure almost all of us has checked out Google Translate at some point or the other, where you're, let's say, typing in or speaking in one language, and the output gets converted into another language. From a source language, we go to a target language. And machine translation, again, is not just limited to only text-based translation. It can even be speech, where you convert the speech to text, known as the speech to text systems, or the text to speech systems, also known as the TTS systems. Question answering has become very popular, where the whole idea is, can you ask a question just like a human would ask, and based on some kind of a knowledge base or a database, can the machine answer back in the form of a human response? And that is where virtual or digital assistants, chat bots, these have become very popular with regard to question answering mechanisms. And again, this is a slide which kind of shows you some of the main aspects of NLP applications in terms of information retrieval, grouping similar documents together, classification, information extraction, so on and so forth. And you can see there are a lot of concepts which are overlapping amongst these with regard to text representation, which is the feature creation, and then you have document similarity, so on and so forth. So the idea here is to understand that there are some key steps in a regular natural language processing pipeline which are very common, and this is something we will discuss in more detail when we go into the NLP workflow. So I've summarized some of the most common natural language processing use cases which are out there in this slide, and you can even check this out later on as a reference. And this is where you can see we have things like text classification. So the idea is to classify or categorize text documents into different categories based on some kind of a pre-labeled data for our historical data set on which we can train our models to learn these patterns. Simple example, which we will see at the end in a case study, is to classify support tickets as to how quickly I should resolve this ticket in terms of the criticality of the problem. Like, let's say whether it's critical, which means immediately solve it, or a high, a medium, or a low priority. Another example could be, let's say, Google News, where they are categorizing different news articles into the relevant sections, like whether this news article belongs to the business section, whether it belongs to the sports section, politics section, so on and so forth. That is where we can also use text classification, where we go through the text content of the news article, check out the headline, the overall description, and we say, does this news article belong to sports or business, and so on. Another example, like I said, is more on the lines of similarity and text clustering, where we can group similar text documents together. And in that way, we can say whether some documents are very similar to each other, whether they are almost similar to each other. That is where duplicate detection and fuzzy matching concepts come into perspective. And you can even build recommendation systems where, let's say, and this we'll look at a hands-on example soon, where let's say we have some movies and we have the description belonging to like the plot of the movie and so on. We can try to find out similar movies based on the plot of the movie and the movie description, and we can recommend those movies given an input movie. So that is where you can build content-based recommendation systems. We discussed about search and information retrieval, where you can build your own custom search engines. You can rank documents based on some input search string or search terms which were entered. You can parse documents, extract the key entities out of them, like entities from health records, legal documents, and so on. You can summarize entire huge text documents to extract the key essence, that is known as text summarization. When you have a collection of documents, that is known as a corpus of documents. So you can try to extract the key themes or the key trends from multiple documents. That is where you use something called as a topic model. We discussed about machine translation briefly, like from speech to text, text to speech, translating from one language to another language, and so on. And we discussed again about conversational interfaces with regard to question answering mechanisms, digital assistants, chatbots, so on and so forth. And the last one, sentiment analysis, obviously, where you're looking at your survey results, your online customer feedback reviews. NPI analysis is again like different organizations do this, known as a net promoter index analysis, where employees give feedback about how well they are finding the company, the environment they are working in, and they try to analyze the text feedback to see the sentiment being exhibited by employees. So overall, again, this is not like an exhaustive list of use cases, but this is definitely the most common use cases in natural language processing, which you will be solving in some way or the other in any company you typically might dive into, let's say as a data scientist, whenever you're working. Let's now look at the standard natural language processing workflow before we dive into some of the detailed nuances of some of the components of this standard NLP workflow. And then we'll look at some hands-on examples also related to this. So overall, this is a standard workflow in terms of trying to tackle any kind of a natural language processing problem. You usually start off with some text documents, where these text documents could be public data or your own private data. And the first step typically is to pre-process these text documents, because what will happen often is that there may be a lot of noise in the data, especially if you are scraping the web or you're getting some external data feeds. So you would need to remove this noise from the data. And we will look at what this noise could be. What are the different types of this noise? Like, let's say HTML characters, extra spaces, new lines, extra symbols, unnecessary characters, so on and so forth. So that is where you would need some level of text pre-processing and standardization to clean, or as they call it, wrangle the text data. And once your text data is pre-processed and cleaned, we go into this. Again, this is an optional step where you may want to visualize some of the key aspects of your data as to, okay, what are the key entities in my documents, or which are the most common words maybe in my documents, which are the most common phrases in my documents, do some level of initial exploratory data analysis. And again, if you are not dealing with a parsing based problem, what we need to do next is to do some level of text representation, also known as feature engineering, representation learning, so on and so forth. So the idea here for text representation is to transform this text data into some kind of, like I said, a numeric representation. And the reason is because typically, like I said, NLP, one of the main components of it is artificial intelligence. And under artificial intelligence, we have this whole perspective of machine learning models and deep learning models. And any machine learning or deep learning model at heart is, as you know, will have some kind of mathematical optimization functions. So in short, what I mean by this is these models don't understand text data directly. They can only work on numbers. Now, let's say you are doing a standard regression problem where you're forecasting house prices. You may look at features like the number of bedrooms, the number of bathrooms, the square feet of the house, so on and so forth. And as you can imagine, these are already numeric features or columns. So you can easily pass that into a regression model and you get the output, let's say, in terms of what is the price of the house, which you're estimating. But in case of NLP problems, your input is not in the form of structured numeric values. You have entire sequences of text data, and you can't dump this text data directly into these machine learning or deep learning models. So that is where, before you go into the downstream task which you have to solve, like let's say classification or clustering or search, so on and so forth, you need to transform this text data and represent it in an appropriate numeric format. And that is exactly what text representation is all about, where you will look at different methods which are being used, from traditional count-based methods to newer deep learning embedding-based methods, to transform this text data into, as they call it, numeric vectors. And once you have these numeric features or numeric vectors, which are the representation of your text documents, you can apply the downstream machine learning or deep learning task, which is basically your modeling phase, where you're either building, let's say, a text classification system, a text recommender, a search engine, so on and so forth. And usually what happens is you may have multiple models, as you know, to try out. So you would obviously not stop at only one model. You may build multiple models. You may build multiple versions of the same model. You may tune your models based on the underlying hyperparameters. So you may have, let's say, a family of models which you try out on the same data. And after that comes the evaluation step, where you select your best performing model. You validate it internally, let's say in your data science team. You validate it externally with your business stakeholders, the domain experts. And let's say once they give you the go ahead, that's where you do what is called as putting your model into production. And that's your deployment stage, where you build your data pipeline, you build your model inference pipeline, you may build a web service on top of that, and you may deploy your NLP model. So that is the overall key steps of the NLP workflow, a workflow for any kind of a typical NLP problem. Now, again, this can vary depending on the problem you're tackling to some extent. Like sometimes you may not need this block. Let's say if you're doing more complex problems involving deep learning, you may need minimal text pre-processing, so on and so forth. But at a high level, these are the key steps which you typically need to solve any NLP problem. Now let's talk about some of these blocks in slightly more detail. We usually start off with the pre-processing block, where we need to clean our text data. So what are the key steps or key methods or key aspects of text wrangling? Like how do we do that? So some of the key aspects here is, one could be removing these HTML tags I was talking about. So especially if you're scraping data from the web, you may end up having HTML tags which need to be removed, because that is not like valid, useful text content. So it needs to be cleaned. You may need to remove extra white spaces and new lines, removing special character symbols. Sometimes you may deal with accented characters. You may need to standardize your text by extracting the root form of the word. That is where you can use techniques like stemming or lemmatization. You can remove stop words, and stop words are basically not useful words, in terms of that they convey very little useful information for your problem, whatever you're trying to solve. And then you can do tokenization if it's needed, optionally do some spelling and grammar checks, so on and so forth. So before we go into text representation, I'll briefly cover a notebook which will show you some typical ways in which we do this. So bit.ly 101. So this is the URL, and if I go here, it will redirect you to my GitHub repository, and you can go to the notebook section. And text wrangling is the first notebook we'll be looking at. And by the way, these are self-contained notebooks, so you can even run them on Google Colab, which gives you a virtual environment for free, and you can play around with this with your own data and so on. So I'll go through this quickly in the interest of time, but the idea is feel free to play around with this whenever you have more time. I'll not cover each and every line of code, because that is there, but the main concepts is what I'll be covering with regard to the inputs, the outputs, the functions being used. So one of the key things is case conversion. So let's say if we have a sentence like this, typically what we can often do is convert it to lowercase, so that every word is in the same case before we go further. That's where typically lowercasing is what is used, but you can even look at uppercasing, title casing, so on and so forth if necessary. But more than often, we lowercase our text to bring every word to the same case. Tokenization is where we break down our huge text document into consumable chunks of information. One of the key things could be extracting the key sentences from our block of text data. So imagine we have this huge block of text data. What we can do is we can leverage the natural language toolkit. By the way, this is an open source package, and you can call the send tokenize function on this block of text data. And as you can see, we get a list of the key sentences in our documents so that you can process each sentence separately, maybe. Now, if you want only the words separated out, what you can do is you can call the word tokenize function here. And that helps you in extracting each of the words separately as tokens, as you can see. So basically, then we can focus on each and every word, and we can try to leverage that. Spacy is another open source library which can be typically used, and it has become very popular recently. So what we typically do is we need to load up a language model, and that is where we load up the English language model, as you can see here, using the spacy.load function. And then what we do is we pass that corpus of text data into the NLP construct. And then if you want the sentences, what we just say is object.text for every object in the spacy construct dot sense. So dot sense is an attribute which gives me each of the sentences. So this is, again, an alternate way of doing things if you are more interested in using spacy. And if you want all the words again, you can just remove the dot sense, and this list comprehension will give you each and every word, by the way. So basically similar results using another library if you're more interested in leveraging spacy. And I would definitely recommend to check out spacy because NLTK is more of, again, a legacy package. Removing HTML tags and noise. So this is where we have, let's say, we have scraped a part of a book, let's say, and you can see there are a lot of HTML tags here, like a heading tag, a paragraph tag, line break tag, so on and so forth. So this is like some non-useful information which should ideally be pre-processed or removed out. And that is where we can leverage the beautiful soup open source package, and we can say that the text we will feed you is from an HTML page. So you use the HTML parser and remove any kind of script tags, iframe tags, and so on, and extract only the key text entities from that. And what we also tell it to do is some additional pre-processing where we remove any kind of new lines, carriage returns, and so on. And once we run this function, you can see that the key text content is extracted out and the HTML tags and everything have been removed out. The next one is removing accented characters, where if you may have some specialized accented letters, you can convert it to a regular English format using the Unicode data library. And in that way, you can have a standard ASCII format across all your text data. The next one is removing special characters, numbers, and symbols. So this is where you can leverage some regular expression patterns to remove special characters, and sometimes optionally you may want to remove numbers and so on. And that is where you can leverage regular expression patterns, saying that if you want to keep only the alphabets and the numbers, you can leverage this pattern saying any character which is between small a to small z, or capital A to capital Z, or 0 to 9, or a space, retain that and remove everything else. Now, if you want to remove the digits also, you say that only keep the alphabets and spaces. So if you use this, and let's say you want to remove the digits, you just pass remove digits as true, the flag. And then as soon as you pass this, it will basically execute this regular expression. And what it will do is, if this is your input text, it only retains the alphabets and the spaces. And if you want to keep the digits, it will remove the special characters. So the digits and the alphabets will be retained. In the previous case, the digits would be removed. So This is where we can leverage the concept of regular expressions to potentially um, keep what is necessary and remove the unnecessary text symbols, so on and so forth. Contractions is another interesting example where we have what is known as a shortened form of a word, where let's say the word is would not, you typically shorten it to wouldn't. How would be shortened to how'd, so on and so forth. And the idea is it's good to expand these contractions as a part of your pre-processing pipeline. And that is where you can leverage this open source package again called contractions, which essentially consists of a dictionary mapping here. And this dictionary mapping is what is used to translate every one of these contractions into its expanded form. And if you call this on your overall document, what happens, as you can see, is all the contracted forms of the words are expanded out. And in that way, also, you can standardize your text data. Stemming is another aspect where we, as you can see, convert the inflected form of a word, so basically different variants of the same root stem, as it is known as, back to that root stem. So like jumping, jumps, jumped, the root stem is jump, so we can translate it back to that root stem. One important part about stemming is it uses a bunch of fixed if else rules. So it'll like say, okay, if it's ending in ing, just remove it, or it's ending in e or ed, remove it, or er, remove it. So the base form of the word known as the root stem may not be a lexicographically correct word, which in simple terms means that it may not be a dictionary correct word, but syntactically it may be correct. So as you can see here for strange, it just chops off the E. So this is not a dictionary correct word, but it is like a syntactically correct word. So that is where if you are dealing with building models or systems which need to be more interpretable in nature, that is where you need to look at lemmatization. Because lemmatization is where it leverages a dictionary to give the base form, also known as the lemma. So that is where we have the WordNet lemmatizer in NLTK. And what happens is you can call this lemmatize function, but to use it effectively, you need to know the parts of speech of the word you're trying to lemmatize or bring back to the base form. What I mean by parts of speech is whether it is a noun, whether it's a verb, adjective, so on and so forth. So as you can see here, cars and boxes are basically nouns. So if you call it with the right parts of speech, you end up with car or box, which is the base form or the lemma. Now, if you're working with verbs, you need to pass the parts of speech tag as a V, and running gets transformed back to run, ate gets transformed back to eat. Saddest, fancier, these are adjectives, they describe other things. So you get back sad, fancy, and the other part is the parts of speech, which is very important. So if you don't pass in the right parts of speech, like by default, if you don't pass anything, it assumes it's a noun. So as you can see here, if we pass in the wrong parts of speech, like ate is actually a verb, if you remember, fancier is an adjective. So if you pass in the wrong parts of speech tag, you will end up with lemmatization not actually happening. So that is something you need to be careful about, that if you want to do effective lemmatization, you need to pass in the right parts of speech. And that is where we have this whole concept of POS tagging, where you can get the parts of speech tag for each and every word. So let's say we have this sentence, the brown foxes are quick and they are jumping over the sleeping lazy dogs. So assuming this is our sentence, if we just lemmatize it directly, you can see it tells us the brown fox are quick and they are jumping over the sleeping lazy dog, which means it has only lemmatized the nouns if you think about it. So like jumping and sleeping, it is still as it is. It hasn't been lemmatized effectively. Why? Because by default, we haven't passed in the parts of speech tag when we are lemmatizing every word or every token in a sentence. So that is where what you need to do for effective lemmatization is you first need to find the parts of speech related to every word. Like this is a determinant, this is an adjective, this is a plural noun, this is a verb phrase, so on and so forth. And the idea here is once you get these tags, you need to translate these to WordNet tags, by the way, and Why you need to translate these to WordNet tags is because we are using the what do you call it, the WordNet dictionary, if you remember, for our lemmatization. So that is where I have built this function. Again, this is completely open source, where you translate these more lower level parts of speech tag to that higher level tag. So as you can see, whatever is a noun or whatever is not a noun, verb, adjective, or um, adverb here, we typically translate it back to a noun by default. And everything else, like an adjective, gets translated into a, and then different forms of nouns get translated to n, and so on. And once you have this, what you do is you call this time the lemmatization on every token or every word along with its correct parts of speech tag. So once we do this, you can see now the brown fox be quick and they be jump over the sleep lazy dog. So each and every inflected form of the word has been accurately translated back to the base form or the lemma of the word. So that is just something to remember when you're doing lemmatization, that parts of speech tagging is very important. And if you don't, again, the reason for showing this is to just talk about what goes behind the scenes. With Spacey, it becomes even simpler. What you need to do is you just need to call word.lemma for every word in your text document, and it'll automatically give you the lemmatized format. The only thing is, for pronouns, it returns the PRON hyphen symbol. So what we do is, if that is encountered, we keep that as it is. So with Spacey, things have become even simpler, where you can just call the lemma underscore attribute and get the right lemmatized version of every word. You don't need to like implement all those complex functions, but the reason for showing that was for you to get like a sneak peek as to what goes on behind the scenes to do this lemmatization and standardization. Going into stop word removal, it's basically like filtering out words which are not very useful and carry little information. So NLTK has a standard set of English stop words like I, me, myself, the, and, typically pronouns, conjunctions, articles, and so on. And you can remove the stop words just by doing like a word by word matching and removing anything belonging to that stop word list. You can add in your own custom stop words. You can remove some stop words as necessary, because at the end you are just matching based on a list of words which are not very useful. So overall, this gives you some perspective on typically how to pre-process text data. Let's dive into the next steps in the interest of time. So next part after pre-processing is basically the text representation is one of the main steps. So that is where we translate these text documents into some kind of a numeric or mathematical numeric representation. And the reason, as I said, is because machine learning, deep learning models at heart use mathematical functions and optimizations. So it can't understand text in its native format. Hence, we need to convert text into some numeric representation, which can be understood by these models. Commonly known as vector space models, because you're translating the text into some kind of vectors, and you end up with a vector space, if you think about it, where you have different dimensions related to the different words in your text or different embeddings you're extracting, and so on. Now, for this vector space model, there are different ways in which you can translate your text to the numeric representations: bag of words, TF-IDF, topic model, similarity. Nowadays, you have word embeddings, document embeddings, and so on. People who are interested in this, just some brief perspectives on this. So typically, traditional ways of representing text, what do you call it, the text data, is in the form of like a count-based model, let's call it, so known as a bag of words. So what happens there is that if you have, let's say, a document of different words, what you do is you usually have a corpus of multiple documents. You try to extract every unique word which is there, and every word becomes a column or a feature. And how you represent every document is you try to count the number of times every word is occurring in that document. And you end up with a vector of counts. That is exactly what bag of words does. It depicts the number of times each and every word occurs in that document. And that vector of counts related to each and every word's occurrences gives you the bag of words vector representation for every document. This will be clear when we go into the notebook briefly. Bag of n-grams is very similar to bag of words. The only thing which changes is instead of considering only words as your features, you can also consider sequences of words. Like let's say two words occurring in sequence, they can become your features also in the vector. Three words occurring in sequence, so these are known as n-grams, where two words occurring in sequence is a bigram, three words occurring in sequence is a trigram, and so on. A TF-IDF model is basically a normalized version of the basic bag of words model, which is also known as the term frequency model, where we try to find out the number of times every word is occurring in a specific document. Now imagine you scale that with the number of times every word is occurring across all the documents. So that is where we normalize the counts using the inverse document frequency, the IDF. So document frequency means the number of times every word is occurring across all the documents. And if you take an inverse of that, it becomes the IDF. So we multiply the term frequency by the inverse document frequency to downplay the effect of frequently occurring words. So imagine if a word is occurring in 99% of your documents, which means its document frequency will be very high. Why? Because it's occurring in almost every document. Now, if you take the inverse of that large number, you can imagine you end up with a very small number. Now, if you multiply that with your term frequency, obviously you end up with a small floating point number. That is exactly how we downplay the effect of very frequently occurring words. And the reason why we do that is you can imagine if a word is occurring in each and every document, it means that no matter what the document is, the same word is occurring. So it doesn't convey much useful information for machine learning models. That's the reason sometimes we use a TF-IDF model. And the fourth one is the document similarity, where we try to derive an attribute or a metric from a base feature vector like the bag of words feature. So this is where we leverage bag of words based feature vectors and try to find out how similar one document is to another document. And this is where we can use some metrics like cosine similarity to find out how similar is a document vector, a bag of words vector, to another bag of words vector document, or how similar is the TF-IDF vector of one document to another document. And we will look at an example of this also soon. This one I won't be covering in too much depth, given the nature of our topic today is more of an introduction to NLP, but feel free to check this out also in more detail as you get time. So the newer versions of text representation models leverage neural networks behind the scenes. And that is where we try to generate dense vector representations of words. So instead of having counts for each word, we represent every word as a vector of some dimension. And that is where, to generate these vectors, we leverage techniques like neural networks behind the scenes. And we have different models like word2vec or glove or fast text. And the whole perspective here is to look at every word and all the words surrounding that word and try to figure out which words are closer to which words are mentioned in the same context with other words, and so on, so that the vector representation of words which are occurring in similar contexts are closer to each other if you use some metric like, let's say, the cosine distance, which means, let's say the most common example, like man is to king is woman is to queen. How we are able to get that representation is, given you are training on a lot of data, like let's say the entire data of the web or Wikipedia, since man or king will be mentioned in similar context as woman and queen, you can draw similar representations using these numeric versions of every word. So the concept of a word, like for us in our brain, we know what a king means or what a man means, but the machine doesn't know it. So how do you make the machine understand that? You make the machine understand that using a vector representation for every word. That's why it's known as an embedding model, where every word is represented by an embedding, which is basically a fixed sized vector. So I'll just go briefly into this examples just to show you some of these concepts as to how they look like, and then we'll move on to some of the hands-on tutorials with regard to some applications of NLP. So if I, hang on. Okay, so sorry about that. Yeah. So text representation with feature engineering. Again, there is a lot of content here. I would recommend you to focus on the key perspectives here. So like, as you can see, we have different documents here. Some of them are related to the weather, as you can see, and they are very similar to each other. Some of them are more related to animals, some of them are related to food, and so on and so forth. So the idea is, what we first do is we need to pre-process this text data. So that is where we do some simple text pre-processing on each of these documents. So how we do that? One thing is we keep only the alphabets with regard to every document. We remove all the special characters and symbols. We lowercase every document. We remove extra spaces. We remove the stop words. So basically what happens is, let's say the document is the sky is blue and beautiful. So this gets lowercased and we remove the stop words. So we end up with sky blue beautiful. I love the blue beautiful sky becomes love blue beautiful sky. So these are the pre-processed versions of the documents. Now, how does the bag of words model looks like? So let's say these are your 8 documents which you have. Once you pass it through the bag of words model, which is available as count vectorizer in scikit-learn, you end up with this numeric representation for your 7 or 8 documents. So what does this mean? This means that this is the vector representation of the sky is blue and beautiful, that document. So to understand it in a more human representational or easy to understand format, this is exactly the representation of your first document. So you can see that every column or every feature of your vector is a unique word in your overall corpus, and the value is the number of times that word is occurring in your corpus. So for the blue beautiful sky, obviously blue beautiful and sky is occurring once, so these are non-nulls, as you can see here with 1. For the 6th document, the sky is very blue and the sky is very beautiful today. Remember, sky is mentioned 2 times. So in that vector, the sky should have the value of 2. And if you go back and see here, you will see that the sky has a value of 2. So this is where this numeric representation is what the machine learning or the deep learning model will use to understand what that document is talking about. So this is the numeric information fed to the downstream application like classification, clustering, and so on. And then you can do n-grams also, where you can say, don't just look at only words, look at sequences of words, like the sky is beautiful, or we are dealing with the beautiful sky. So since beautiful and sky occurs in sequence, that is a bigram. So it occurs 1 time in the 2nd document. So that is where you can look at sequences of words. Similarly, TF-IDF model will scale every value or every frequency, and you can see you end up with some floating point numbers using the TF-IDF vectorizer. And the idea is, once you have these vector representations, I can say that, hey, looks like these 2 documents are very similar if you look at the non-null values. So wherever it is non-null, it is very close to each other, and wherever it is null, it is very close to each other, except some cases where it may be a bit further. So what happens is, once we look at these 2 documents, we can use a mathematical metric like cosine similarity, and we can quantify this in terms of a number from, let's say, 0 to 1, as to the closer to 1 it is, the more similar these 2 documents are. And we end up with a pairwise similarity, where we compare how similar document 0 is to document 1, how similar document 0 is to document 2, document 3, so on and so forth. And you end up with a metric or a matrix like this, where every metric here is how similar document 0 is to 1, similar 0 is to 2, and so on. And you can see that this diagonal is essentially something we can ignore, because every document is obviously similar to itself exactly. So it's 100% similar. But what is of our interest is, we can see document 0 is 82% similar to document 1, but it is not at all similar to documents 2, 3, 4. It's not very similar to document 5, but highly similar to document 6. So once we get these quantifiable metrics or values, we can use some downstream application like clustering to say, hey, looks like these are my document similarities. Can you group our documents together in terms of what is very similar to each other? So if we have these similarities being computed in the right way from these vectors again, what the clustering algorithm can do is, it will try to group documents 0, 1, and 6 together. It will try to, let's say, group 2 other documents together, like let's say document number 5 and 7 here, so on and so forth. So that is where we can leverage an algorithm like k-means. I'm sure a lot of you may have heard about this, where it uses a partition based method to cluster similar items together. And you can see, even if we didn't have this category, and if we only had this similarity vector, that is where we can leverage, sorry about that, that is where we can leverage the clustering methodology. And you can see that document number 0, document number 1, document number 6, they are all grouped under the same cluster. And document number, let's say 5, as we talked about, and document number 7 is talking about animals. So they are all grouped under the same cluster. So this is where the document similarity becomes a very powerful metric, especially for recommendation based systems. And that is something we will look at shortly. So coming back to our presentation, what are the downstream machine learning or deep learning tasks which you can do after you do the feature engineering or the text representation? This is where you can do, like we discussed, classification. You can build text recommendation systems. You can do clustering. You can do topic modeling. You can do sentiment analysis, semantic analysis, and so on. And this is where, based on the kind of task you're trying to do, like regression, classification, search engine, so on and so forth, you use the right machine learning or deep learning models. Now, again, stepping back a bit, if you're trying to think about solving NLP problems in the industry, one of the key things you need to remember is how do you frame these problems? Because in the industry, no one will be coming to you saying that we need to build a classification model or we need to build a regression model. They will just say you, this is the kind of data we have, and this is the high level problem which we are trying to solve. So how do we frame this problem? That is where you need to figure out whether this is actually a classification problem, or whether this is an entity extraction problem, whether this is a search problem or recommendation problem. So framing the business problem becomes more important than trying to figure out whether I should use Pacey or TensorFlow. So this is something all of you should remember, that this is one of the real world challenges in the industry. Since you will be dealing with non-technical, let's say, or business oriented folks, they will not know like what is the task. So that is where you need to be able to translate the business problem into the right data science problem to know whether this is a classification problem, an entity recognition problem, so on and so forth. And the next step is basically debugging. So most tutorials typically will stop at X% accuracy if you think about Kaggle, so on and so forth. But in the real world, how do you know that when you should stop training your models and when is it ready for deployment? So this is where you get a dilemma as to, do I spend the next 1 month tuning my model to get a 1% increase in accuracy, or do I deploy my model? So these are some of the challenges which you will face as you go into tackling NLP problems, because it is very difficult sometimes to quantify the performance of your models in terms of accuracy, precision, recall, and so on. So my advice to you would be, you won't really know how bad it is unless you try out. So that means don't over invest your time in dealing with a static data set of like a typical train test split and trying to over optimize on it to get a high test score or a cross validation score. Once you reach an X% performance and you see it's not improving too much, I would say deploy it as a pilot and work on real world data which keeps entering into your pipeline, and see how your model is performing day in and day out. That is where you will see that the performance may actually drop. So don't go just by the accuracy of your static data set. Work on the dynamic real-time data which comes in, and accordingly improve your system, improve your model. So these are some of the key caveats which you may come across in the industry. So just to keep this in mind. Now let's go on to the hands-on tutorials briefly before we talk about or end our session with the case studies. So we will look at two hands-on tutorials today where we'll go through some code and try to look at some kind of a perspective of a real world problem. So the first problem we will look at is a movie recommendation system. And the whole perspective here is, given that we have a complete database of movies and the description of the movie. So what do I mean by the movie description? What I mean there is that we will have like the tagline of the movie, some brief about the plot of the movie, the characters, the story. And the idea here is, can we find out based on this description that which movies are similar to each other? If you remember where we found out the animal-based documents are similar using cosine similarity, or the weather-based documents are similar, can we apply that same concept here to figure out that which movies are similar to each other, so we can recommend movies to users. And the second one will deal with some standard sentiment analysis problem where we look at product reviews given by customers and corresponding ratings as to whether the product is a good product or a bad product. And the idea is, by looking at that review text which a person is writing, can we express what the person is feeling about that product, that whether that was a good product or a bad product. So this is more of a information retrieval slash text similarity problem, if you think about framing the business problem into a data science problem, and this is more of a text classification problem. So let's talk about our first hands-on example, the movie recommendation system. So these are our key steps which we will be following. We get our movie data set. We obviously have to clean the movie descriptions briefly because it is text data. You need to do the text wrangling. Remember that pipeline we talked about, the workflow. And once we clean these descriptions, we obviously need to do the text representation step. That is where we build these TF-IDF feature vectors for every movie description. Then we try to figure out how similar every movie description is to all the other movies. That is where we use the pairwise document similarity by using, let's say, cosine similarity. And once we know how similar every movie description is to the other movie descriptions, given that I say that, okay, I've watched the movie Minions, can you recommend a few movies for me? That is where we will leverage that similarity matrix and say that if your movie is Minions, maybe these are the top 5 movies you might want to watch. So these are the key steps in our movie recommender system. Let's jump right into the code. And by the way, these are again available in the GitHub repository. I'll be sharing the link again at the end of the session. So feel free to play around with your own data set maybe in the future. And this is the basic concept of it, that given that I have watched a particular show or a particular movie, can you recommend some similar movies or shows to me? That's the whole aspect of recommendation systems, as you know about it. So this is a simple content-based recommendation system because we don't have like a user history that, okay, if user A has watched movies A, B, and C, and user 1 has, let's say, watched movies A, B, and C, and user 2 has also watched movies B and C, recommend movie A to the user 2. So we don't have that kind of history. We only have some content-based history. So this is where we are leveraging an open data set known as the TMDB, the movie database, and it has overall 4,800 odd movies. And there are various fields again related to the movies. The key fields of our interest will be the title of the movie, which is basically the movie name, obviously. Like I said, the tagline of the movie, which is like a brief one-liner for the movie, and the overview of the movie, which is a detailed perspective of the plot of the movie, the story, let's say the characters, so on and so forth. So the idea now is, can we leverage this text information to figure out how every movie is similar to the other movies? So these are the key steps, like I mentioned before, even in the slide. So first step is to pre-process the text documents, and that is where we will be what we'll do first is, we have 2 fields, by the way, tagline and overview. So we combine these 2 together into one text field. And how we do that is we create a new field called description, and we say that just simply append the tagline and the overview and separate it by a space. So you get the point. The 2 text fields are being merged into one field called description. Now we want to find out how similar one movie description is to the other movie descriptions. So the text preprocessing, again, standard steps. We retain the alphabets, the numbers, and the spaces. We lowercase our text. We remove the spaces. We fix our contractions. We remove the stop words. And once all of this is done, we basically call this on our entire data frame. And we end up with 4,800 pre-processed movie descriptions ready to go to the next step of our pipeline, which is the text representation. So that is where we extract the TF-IDF features, if you remember, where we extract every word. And in this case, we are extracting every word as our feature as well as every bigram. So 2 words in sequence as our features. And we end up with 20,000 odd features, or the size of the feature vector of every movie description is a vector of length 20,468. So this is the shape of our data, where every row is a movie and the columns is basically the words and the bigrams and the number of times they are occurring for every movie description. So once we have the TF-IDF features extracted, what we do is we want to find out how similar every movie is to the other movie. So that is where we end up with a matrix of size 4800 cross 4800, which means 4,800 rows and 4,800 columns. And like the first row basically tells me how similar is movie 0 to itself, obviously 100%, how similar it is to the first movie, second movie, third movie, and so on. So what I will do is, if someone tells me, recommend me the top 5 movies, if I've watched movie with the ID 0, I will look through this vector and I will find out the top 5 movies with the highest similarity score. Like in this case, movie 10 is 2.5% similar to movie 0. So in this way, I can build that recommendation system. So just some basic housekeeping here again with regard to extracting the key movie names. So let's say I have watched the movie Minions and now I want you to recommend some movies to me. What I do first is I find out where is the movie Minions in my similarity matrix mapping. And I figure out that it is present using numpy.where. I figure out that the 0th position of my matrix belongs to the movie Minions. So what I do is I extract out this complete similarity vector, which means I extract out how similar all the 4,800 movies are to the movie Minions. And once I extract these similarity metric numbers, what I do is I basically sort it in the descending order. So by default, sort will sort in the ascending order. So I do a minus to sort in the descending order. And as you can see, I'm using the arc sort function of NumPy. So instead of returning the similarity value, I tell it return the top similar positions of the matrix. So that is why it tells me movie 33 and 60 are the top movie IDs, which are most similar to movie ID 0, which is Minions. So once I do the mapping based on my list of movies, it tells me that Despicable Me 2 and Despicable Me are the top similar movies which are recommended to you if you have watched Minions. And if you think about it, it makes sense given that all of them are from the same franchise. And this is how you can build a generic function and pass in multiple movies. As you can see here, some very popular movies out there. I'm pretty sure all of you must have watched most of these. And you can see that, okay, if I've watched Minions, you should watch Despicable Me. If you've watched Interstellar, these are the movies. And you can see for franchise-based movies, it'll recommend you similar movies like the prequels or the sequels in the same franchise: Pirates of the Caribbean, Planet of the Apes, Hunger Games, Terminator. So you get the point. So using some simple yet powerful constructs of TF-IDF feature engineering, text preprocessing, document similarity, you can build an effective recommendation system. And you can even improve upon this by using deep learning based feature representation methods like we discussed, like word2vec or fast text. The core concept is, instead of TF-IDF, you use a more complex feature representation model, but then you can again use cosine similarity to find out how similar every movie is to the other movies, and then you can get accordingly really well recommended movies based on the movie description. So hopefully this gives you some level of understanding as to how, using some really not too difficult but powerful concepts, you can build a complete system, in this case a text similarity based movie recommender. Coming to the next example, this is where it's all about recommending a product based on the review which a person has given. So whether it's a good product or a bad product. So this is a supervised learning or a classification problem. And the key steps which we will follow here are basically these. So we get our data. That is the first step. We download our data. We get the data frame from that data by loading it up. We do some basic data pre-processing again with regard to pre-processing the text review which every person has given for different products. And then we basically follow what is known as the iterative process in machine learning by trying out different types of features and building a classification model on these features to see how good a classification model I can build. So as you can see, we will try out some simple NLP count based features. We will try out some sentiment based features, and we will finally try out some of these bag of words based features, which will be again extracted from our text reviews. And we will try to build some classification models on a combination of these features. And every time we will see whether we are able to build a better model than the previous iteration. So this is where we will do what is called the train, evaluate, and reiterate by building different classification models. So let's jump right into it. This is the last notebook. Okay, so this is again a self-contained notebook. You can run it on Kaggle also potentially. So the data set again is an open data set, and as you can see, it's available in Kaggle called the Women's E-commerce Clothing Reviews, where a lot of e-commerce products are there with regard to clothing, women's clothing, and people have reviewed these products by giving a text-based review, and they have also given a rating. So we have converted it into a simple recommended variable, if you think about it, where if the rating is more than 3, it's a recommended product, which means the um, product is a good product. And if it's less than 3, it's basically less than or equal to 3, let's say, something like that, it's a bad product. So that is where we translate our problem into a simple yes or no problem, also known as a binary classification problem. So how do we frame this problem? It is very simple. By looking at this text, can I say whether it's a good product or a bad product? That is my binary classification problem. First step, remove all the records where there is no review. So in many cases, the review is blank. So unfortunately, you need to remove that because you can't predict if you don't have any review, obviously. You get the point. Now, the next thing is we need to look at the class distribution. That is what we typically always do when we get started with a classification problem. And as you can see, it's pretty imbalanced, almost like a 1:5 ratio or even more than that, where the number of good products or recommended products are obviously much more, almost more than 5 times, versus the number of non-recommended or bad products. First step after, next step after the initial distribution analysis is to do a train test split, where we extract out our training data, which is 16,000 or 17,000 odd reviews, and the remaining 5,600 reviews are my test data set. You can look at the class distribution again if necessary, but now let's convert this text data into some numeric representations. So what we first do is we start with some basic count-based features, which means look at this text review and extract some key entities in terms of count and density based features, which means find out the number of characters, find out the number of words in the review, the ratio between words to characters, also known as the word density, which is basically the character count by the word count. Okay, and then number of punctuations, number of words which are starting with the uppercase, that is your title words, number of words which are completely in uppercase, that is a uppercase word, which means like they may be expressing some strong emotion. So in this way, these become our features which will go to our initial classification model, which we will train. So the classification model we select is, I guess, the most basic model which you learn when you start off with classification, where it's logistic regression. And we train a standard logistic regression model by fitting on the training features, which is basically, by the way, these features. And then we predict the performance on the test data. Again, this is a simple problem. It can be complex, but we are not doing any model tuning and all those perspectives here. We are just trying to show you how the model is improving over time with different features. So as you can see here, once I predict on the test data, which if you remember was 5,600 odd reviews, and the ratio was like a 1:5 kind of a imbalance, you can see that for all the bad products, so all the bad products or bad rated products, we are not able to predict a single one of them. That's why the precision, recall, F1 score, they're all zero. And just to give you again a brief context, I'm sure most of you are aware about this, but precision is basically the positive predictive power of a model, which means out of all my predictions, so out of all the times my model is predicting that, okay, this is class 0, how many of those predictions are actually correct? That is precision. Recall is the coverage, which means out of 1271 samples belonging to class 0, how many of those samples was my model able to predict? That is the recall, also known as the hit rate. And the F1 score is the harmonic mean of the precision and the recall, like an average metric, if you think about it. So obviously, higher these numbers, the better it is. So you can see here that for class 1, which is the good products, obviously we have more data and the performance is not too bad. It's pretty decent. But it's basically a useless model if you look at the confusion matrix. And the reason is these 1271 bad products are all predicted as class 1. So essentially, it means this model is predicting every review as a positively perceived product. It's predicting every product as a good product. So it's essentially like you don't even need a model, then you can just take in any review and say this is a good product. So this is basically a useless model. So which means these features are not really helping us separate out between the good and the bad perspective of things. So what can we do next? This is where we can look at sentiment, because reviews are pretty subjective, which means they are opinionated. And that means people are expressing some strong opinions, emotions, or feelings about these products which they are reviewing. So it becomes a classic case of sentiment analysis. And the idea here is we can leverage a open source library here called TextBlob, which uses what is called a lexicon-based sentiment analyzer, which means it will use a huge database of words, phrases, look at the parts of speech, look at the word itself, and it will try to rank rank or score a review based on all the positive words and the negative words which are occurring by looking up in its dictionary, and it will give an overall polarity score as well as a subjectivity score. So what that means is polarity score is between the range of -1 to +1. So obviously, more positive sentiment being expressed by the person, the higher the polarity is, closer to 1 it is, and the more negative emotion being expressed by the person, the lower the polarity is, or closer to -1. And the subjectivity is the strength of the emotion being exhibited. So let's say if I'm looking at let's say a press release, usually it will be like a factual document. Like let's say I'm saying the sun rises in the east or the sun sets in the west, things like that. That's like I'm not really expressing any emotion. That's like a fact. So that is an objective document. But subjective is when I'm saying that it is really hot today or I hated this movie. So that's like a strong emotion. So it is a subjectivity should be higher or closer to 1. So using these two numeric features, we can maybe add it to our feature set and see how our classification model performs. So that is where you can see that if this is a sample review, this is an amazing pair of jeans. Its polarity is pretty high and its subjectivity is also pretty high. And let's say if we are dealing with this review, I really hated this ugly t-shirt. So what happens here is you can see polarity is -0.95, which means that it is pretty negative. And subjectivity again is high because strong emotions. So what we do is we extract these features, as you can see, polarity and subjectivity for every review. And now we build a classification model using these features. And once we build this, you can see on our test data, we are able to now predict 27% of our bad reviews. So that means out of 1271 bad products, we are able to predict them bad correctly, 339 of them, which is not bad. Earlier it was 0. Now we are able to predict 27% of them. And precision is also pretty decent with around 69%. So The idea is now we are at overall 77%. Can we improve this further? So this is where we look at the bag of words based method, which we discussed earlier. So that's where, again, doing some basic pre-processing on our text documents with regard to keeping only the alphabets, removing some spaces. Here I did stemming to save time. You can even try out lemmatization. And then once your text documents are clean, what you do is you get the bag of words vectors, and that's where I'm using the count vectorizer. And you can see every word here becomes a feature now, and these values are the number of times that word is occurring in every review. And this becomes our complete feature set now. So we have the counts, we have the sentiment, we also have the number of times every word is occurring for each and every review. So a total of almost 8,500 features for every review. And then we fit a model on this feature vector. And you can see now from a 27% recall, it has jumped to 70%, which means we are able to predict 70% of the bad products as bad. And that is pretty good. And our precision is also pretty decent at 76%, given the imbalance. And you can see for good products, the performance is really pretty nice here, almost 92 to 93% performance. So overall, you can see it has switched now. So out of 1271 bad reviews, we are able to predict 890 of them correctly, so close to 900 of them. And that's where our overall F1 score jumps to 88%, and that's pretty decent. And of course, you can play around with this further by trying out other types of feature engineering methods, bigrams, embeddings, other aspects, and again, reiterate in the same way by trying out a logistic regression model to see if the performance improves. So hopefully this gives you some perspective where we basically tried out different types of features, and we trained and we evaluated and reiterated to get to a better performance from a baseline model. So I think it's almost 1.5 hours. I'll just dive quickly into the last part of it, the industry case study, before we wrap up, and then we can do a brief Q&A. So the industry case studies basically cover some of the problems I've solved quite some time back. The whole perspective is all about ID service management. I won't go into the process side of things due to the interest of time. Let's dive into the business problem before we motivate the way in which we could leverage AI. So incident management is one of the key problems of any enterprise, if you think about it. The basic idea is an incident is whenever something is going wrong in the enterprise environment. Like, let's say your laptop has stopped working, or network connectivity is affected, or let's say a data center has gone down. So the idea is in incident management, how quickly can you resolve that problem and restore business as usual? And the focus is on minimizing the impact to business operations and ensuring the best possible level of service and meeting the service level agreements based on whatever is stipulated. So these are the key steps in the overall incident management process, where you start with logging the incident, where you as a user or you as an employee can go and call on the phone to a support agent, or you can type in and fill up a ticket, and that is where the ticket gets created, where the agent can create the ticket for you based on a phone call, or you can yourself type in and create a ticket. And once the ticket is created, what will happen is it will go to the queue, and there will be support specialists who will be sitting and manually reading through your ticket. And then it will do some prioritization, saying that, if you remember from the last time, whether this is a critical problem, needs to be resolved immediately, whether it's high, medium, or low. And once they do that, what they will also do is they will try to analyze who can resolve this ticket, whether they should go to the network operations team, whether they should go, let's say, to the data team, so on in general. And that is where the ticket would get routed to the right support team. And then another specialist would look at it, they would solve the problem, they would tag the root cause to the problem, and then they would, let's say, close the ticket. So you can already think about some of the manual bottlenecks in this process with regard to analyzing and assigning the root cause of the ticket so that a right support specialist can look at it and solve the problem, looking at how quickly the ticket should be solved. That is where the prioritization. So these are the top use cases for NLP slash machine learning slash deep learning, which can be used here to improve your productivity, where you can automatically try to categorize the priority of the incident. You can automatically try to predict the root cause of the incident. And given you have enough historical data where you know what was the solution which was used to solve the ticket in the past, you can maybe build a self-healing system itself, where if a new ticket description or a new ticket comes in, you can automatically suggest the best possible solution which can be used to resolve that ticket. So let's briefly cover this, and that will give you some perspective. So predicting the incident root cause and the priority, this is where we are basically trying to say automatically what should be the criticality of the incident and what should be the priority of the ticket. So basically the idea is
I guess Dipanjan just dropped off. He must have an internet issue on his end. Let's just give him a couple of minutes to come back on.
hey, am I audible?
Yes, you're back. Yes, thank you.
So, sorry, I got lost for a
Not a
second.
problem.
Sounds good. Yeah, I don't know how it got disconnected, but can you tell me, was I covering this one, the last thing, before I got disconnected?
Sorry, you'll have to reshare your screen.
Sorry about that. Let me quickly go to this. Hang on. Yeah, so what I was covering was this. So can you tell
That's
me
right.
which was the last, this one, right?
Yeah, this is the one.
Got it, got it. So let me quickly do this. Yeah. So basically, the idea is it leads to a lot of manual effort and wasted efficiency, and distracts them from their true problems of actually resolving these tickets. So the idea is how can we automate these processes, and based on the historical ticket data, where we already know what was the criticality of the problem, let's say from the past 2 years worth of ticket data, can we say in the future, if a ticket is coming in with our models, that okay, this ticket looks to be a high priority ticket, or this ticket looks to be a low priority ticket. So that is where we leverage our classification models, which we can build on this by looking at the ticket description and the corresponding labels. So this is where we can leverage natural language processing by looking at the historical ticket data. Again, remember, this is already labeled data. So we will look at the historical ticket data with already categorized root causes or the priority of the ticket. And that is where, how do we do this? We parse and process the ticket description. We can look at other structured fields also, like the location, the product, and so on. We generate the text features like we talked about, the bag of words or the embedding, so on and so forth. And then we build some classification models on top of that. And this is just to motivate how the kind of data looks like, some sample data where you may have the root cause, which was assigned manually by the agent, the short description. There could also be the priority, whether it's critical or high, medium, low. And you want to build a model on top of this label data. So in the future, if someone says Outlook cannot be started, you can say that, okay, this is a critical problem and the root cause is, let's say, cannot start Outlook, something like that. So this is where, this is the kind of a pipeline which we followed. And you can see this is very similar to that workflow slide I covered earlier. So that is where we first do some text wrangling or pre-processing by removing special characters, stemming lemmatization, stop word removal, tokenization, those kind of aspects. Then we do the text representation piece where we can, again, do that iterative thing we talked about in our last tutorial, where we can play around with bag of words features, TF-IDF, look at embeddings. Sometimes when we have a lot of features, to prevent overfitting, we can do things like dimension reduction. So this is, again, an optional step where you can look at principal component analysis or singular value decomposition to reduce the dimensionality. And you can play around again with different supervised learning models once you have the text in a numeric format, where you can look at linear models like logistic regression, SVM, your tree-based models like random forest, decision tree, gradient boosting. You can even look at deep learning models. And once you try out different models, we do the model evaluation where we see what is the confusion matrix, what are the classification metrics, precision, recall, F1 score, if you remember, AUC. And obviously, besides the internal validation, we also validate with the domain experts by actually deploying it on the field and seeing that, okay, if this is my short description and this is my predicted reasoning, does the support specialist agree with it? So based on this, we can go back and look at our misclassifications, and we can try to debug our models, and we can try to see what is going wrong and improve on it. So remember always that in the real world, don't just focus on only the numeric metrics or the data science piece of things, but also focus on actually validating it with the external users or the business users. The other part is the incident resolution. So far we talked about the earlier part of the queue, if you remember, where we are automatically prioritizing whether it's a critical problem or not. And we are automatically trying to say which queue it should go to, whether it's a mail cloud issue or a Skype issue or a network issue. But now the idea is, if we have, let's say, 5 years worth of historical ticket descriptions and other fields, and we have also, let's say, a knowledge article or a sequence of steps which was used to solve that problem, can we automatically close the ticket itself by solving that problem in the first place? So this is where we can reuse some of these components, and we can leverage a methodology where we try to map the problem to a known solution. And you can imagine that if it is sometimes, let's say, a script based service which can be triggered to solve the problem, it can automatically get triggered given that our model has enough confidence. So basically what we're trying to finally achieve is that end goal of a self-healing system. But this is where you need to remember, it is not that straightforward that any ticket which comes in, you automatically trigger a script and start self-healing, because if you trigger the wrong script, it can sometimes be catastrophic. So if the model has enough confidence, that is the key thing to remember, because this is where you need like a human in the loop process, where if your model is not having enough confidence, you pass it to the external users or the support specialist, and they will decide whether your model is correct or not. And that is where the final end result of this is, once the model is deployed, given that a new ticket is coming in, it can automatically recommend a solution for you, and it can even run that. Let's say if it's a automatic script which can be used to resolve the problem. And that is where we had two scenarios here. One is, given that someone has already filed in a ticket, can you recommend the solution to them and they can fix it themselves, or the script runs by itself, basically the self-healing perspective of things, where it predicts a potential knowledge article or runs the script related to the solution to solve the future incident. And the other one is more of a self-help portal kind of a scenario, where we build a custom search engine. You remember we talked about information retrieval initially. So this is where instead of someone opening the ticket, they can just type their problem, and we will, based on the historical data, do the text similarity, if you remember, and show that, okay, based on your input query, these are the top 5 similar tickets which had been opened in the past, and these are the solutions which were used to solve it. So essentially it becomes like a self-help portal where they can select, okay, this looks to be my problem, let me follow these steps and solve it by myself. And if they're not happy, they can open a ticket, and then we go into this trigger, or we enable the human in the loop process. So that is essentially where we are looking at scenario one, where we already have a classification model which was built. In this case, we used a recurrent neural network, and based on the past feature representation and the resolution knowledge articles, we have built a model. So in the future, if a new ticket comes in with the description, we basically predict what could be the knowledge base article for resolution and the confidence. And this is used by the support specialist to manually resolve the ticket if the confidence is low. And the other one is the self-help system, where we are indexing all our historical data related to tickets and the solution which was used to solve those tickets, so that in the future you have a search engine interface leveraging Elasticsearch and natural language processing. So someone can type in their query and you will say, based on the last, let's say 1 year worth of data, these are the most similar problems to your query. And you can maybe look at the solutions provided for these and follow that. And if you're not happy, open a ticket. So that is where the reason for doing this, you can imagine from a business perspective, is to reduce the number of tickets created and in turn reducing the mean time to resolution, and obviously improving the operational metrics or the key performance indicators. So it's not like this was done just for the sake of it. Everything, again, remember, you have to tie it back to the business problem. So overall, yes, that is mostly what I had to share. I went a bit over time, but hopefully this was useful, and again, open for any questions.
Hi, Dipanjan. Sorry, I dropped out just as you were finishing there. So
No issues, no issues. Yeah.
thank you very much for your talk. Questions? Um, anyone? I've got one question that had come in with regards to removal of special characters when you were talking about HTML, and the fact that sometimes the structure itself of the HTML can provide some significant information about the text itself, right? And so, is it always a good idea to throw out, those tags, or when is it useful, and how do you deal with it?
Right. Totally agreed. So again, that is exactly where we frame the problem and we decide on the sequence of steps. So absolutely, in some cases, we may need to, let's say, extract the list tags, right? Or extract the checkboxes and see what was selected by the user from a form response, aspects like that. So that is where we may need those HTML tags to apply some regular expressions or pattern matching, and then maybe do the pre-processing. So yes, in short, you don't just blindly apply it. When you want to focus on specific structures in your HTML based on the tags and extract the right information from that, you definitely need those tags. But once you have the right information, then you can remove them if necessary. So it'll be on a case-by-case basis.
Great, thanks. Rishupal has a question. Do you want to unmute yourself and just ask it? Rishupal?
Yes, sure. Just a second. Hi, Dipanjan.
Hey.
Actually, I just saw a last notebook.
Mhm.
There were various basic features were used for analysis of the review, like care count, word count, and density. How we actually like decide on the basic features, like of these kind, and also I can see that when you predicted uh, the very first model, only these features were used, but were not really useful in the prediction. Like we didn't even get one correct bad review. So how to decide on these features basically, like, and how to.
So yeah, I get your point exactly. So that is where we need to follow this iterative process, where initially we start with a basic set of features that could even be the bag of words features, by the way. But so count-based features are initially the simplest ones. That is why, just to showcase that, I had started with that. So it'll depend on your problem again. Like, let's say you're dealing with entities, you may need to extract features related to how many people are being mentioned, how many, let's say organizations are being mentioned, things like that. So how we decide is we see the performance. Typically we see the precision, the recall, and usually if it's not contributing at all, we can drop those features also. Not that you have to continue including them, but this is where we leverage a combination of the domain knowledge and the NLP knowledge as to, is this a sentiment analysis problem? Then extract sentiment based features. Is this a classification, traditional keyword based classification problem? Then you use bag of words. Is this a sequence based problem where, let's say, some words are mentioned afterwards which can be related to something mentioned before? Then you can look at embeddings and, let's say, sequence based information. So based on the kind of understanding of the problem and the context of your problem, you can try out different types of features and even different types of models. Like here I just use logistic regression. You could even train other models and see which is the best performing model. So to make the final decision, you have to ultimately rely on the metrics of precision, recall, or what is useful for your case, maybe log loss, so things like that, and make a final decision. Of course, it cannot be, let's say, always perfect, because sometimes you may need to use some features which are really contributing and helping your model. So that is where absolutely you need to make a final decision and make a final decision based on the context of your problem.
I can the others hear me? I'm not sure whether Dipanjan's dropped off or my connection is out. Okay.
Yes,
So I
we
guess
can hear you, sir.
Dipanjan's dropped off. Let's just give him a second. Hey, Dipanjan.
Hey, sorry, not
I was
sure
doing
what's
something.
going on, but yeah.
No
So
worries. Carry on.
just to brief again, basically you need to try these combination of features and depend upon the metrics of precision, recall, F1 score, and basically decide what features are really contributing and helping your model, and ultimately make that decision.
Got your point, Dipanjan.
Uh,
Thank you so much.
Explainable, AI contributing to that. One of the question, part of that question was about, what features are important really. Do you think that some of the explainable AI work can contribute there?
Yes, absolutely. Because sometimes people, especially business folks, might need to understand which features are really contributing. So that is where absolutely I agreed, where we can, especially let's say if a random forest model, or let's say even an XGBoost model is giving you a high performance, sometimes you may need to look at a model agnostic way of interpreting that which are your important features. So that is where absolutely explainable AI is definitely becoming bigger. And now we are having explainable AI methods for, let's say, CNN based text classifiers, RNNs, even let's say transformers for that matter. So it can definitely help us explain the more complex deep learning as well as machine learning models for NLP. Yes.
The next question is by Nikita Agarwal. Nikita, do you want to ask that question? Okay, let me just ask that. So she's asking about Indian languages and how, given that the grammar rules are different, how do we deal with Indian languages when it comes to NLP?
So basically, in short, you need a custom tokenizer to understand whether the language is read from left to right or right to left. You need to read in that sequence. You need to process in that same way as you generate the representation. So there are some packages like INLTK and even some of the newer transformer-based models where people have already parsed through these languages and done the due diligence of building tokenizers, building entity extractors, building embedding models, and you can leverage some of these right out of the box to do it. Otherwise, what would happen is you would need to build those rules. Like as we know in English, we go from left to right, we tokenize it accordingly. So you need to build these custom tokenizers and processors if you want to process, let's say, non-English languages, especially in the context of Indian languages. But now, thanks to open source, you can leverage a lot of these packages where they have done the hard work for you.
So another question from Tanuj Sharma, who's listening on the YouTube live. So I'll read this out for you. System can also handle ticket attachments like documents, PDF, image, screenshots, etc. I guess that was a comment by you. Won't it increase overall processing time?
Absolutely. That is where you need to evaluate a simple versus a complex system and see how your accuracy is performing. So if you really want to make it complex, it can be a multimodal system where you use the text description, extract the features, use the structured fields, extract or use them as features, read in the attachments, extract the right content from the documents or PDFs, maybe use a CNN based model to extract key features from the images, which are the attachment screenshots, let's say. And you can combine all of these and build a multimodal classifier, but that is where processing time would increase a lot. So you need to evaluate and see what is the trade-off in your accuracy and whether you need that extra features being processed and fed into your model. And based on that, of course, it can be a really complex model or it can be a simple model. So based on the performance, we would need to make a final call. And by performance, I mean not just the prediction performance, but also execution time, latency, and processing time.
Cost, right, of prediction.
Absolutely,
Trying
yes.
to save money. Okay. And the next question by Yash: when carrying out the sentiment analysis on tweets, is it possible to detect sarcasm, and how would it affect the performance of the model?
Yes, I think I had discussed this a while back. So sarcasm detection, definitely tough. There are a few research papers out there. So you can go to paperswithcode.com and you can definitely search for sarcasm detection. There are a few neural network models which have been used, but again, a lot of them have been based on label data where they are trying to establish relationships between word sequences and so on based on what is sarcastic versus non-sarcastic, just like fake news detection. So if you have that kind of a data set, it is easier versus, let's say, trying to do it in an unsupervised approach. But yes, when you're dealing with Twitter data or any kind of social media data, sarcasm detection or even, let's say, fake news detection for that matter becomes an important perspective. Do we have models right out of the box which can do it? Not really. Like, even if you take the latest transformer models and you pass in a really sarcastic review, it will still say it's a positive sentiment. By the way, it can handle negation but still not sarcasm. So that is where I guess right now most of it is pointing towards supervised approaches where you can fine tune and build some models, but I haven't seen much with regard to completely unsupervised approaches which can say whether it's sarcastic or not yet. So I would recommend check out those papers, but a lot of it is to again deal with supervised approaches.
So, I mean, I guess a related question to this is, when we talk about Twitter and doing sentiment analysis on Twitter, a lot of the words have been abbreviated and it becomes out of vocabulary for the kind of libraries you were using for polarity detection. So how do you deal with that?
So typically, abbreviations and so on, at least for us, we usually have a custom vocabulary. So we basically do what is called a synonym expansion. And let's say we are using a search engine interface. We have a synonym file, which will help us expand it. But in short, I mean, unless you know the abbreviations for that matter, it's basically like a very manual process where you need to do the abbreviation and basically expand it based on a mapping interface. Now, assuming you had enough data, you can even train some kind of an encoder decoder model also in the future, which can maybe automatically do it for you. But the key here is basically that label data, unless you have it, at least for us. It's not like automatically intuitive in a way to handle that. So that's how typically we do it. Yeah.
Okay. The next question from Karanjot: in order to tackle imbalance, can data augmentation be done in the case of text data as well?
Yes, so that is a very interesting problem, absolutely. And one perspective is yes, once you convert your text data into a numeric format, you can look at traditional approaches like AdaSyn or SMOT and try to generate more samples of data. But again, in my opinion, that's not the most effective way. There are document augmentation examples coming up with the recent, you can say, expansion into transfer learning, where you can use sequence to sequence models, you can use transformers, and you can generate what is known as the paraphrases. So for one sequence, or let's say one sentence, you can generate alternate representations of the sentence. So basically, it talks about the same thing, but in a different way. So yes, in that case, you can leverage some of that for data augmentation, but I would say it is not as mature as, let's say, something like text classification, but that is something which people are definitely diving into. The most simple approach is you replace words by synonyms and you generate a new form of the sentence. But the more complex approach is you use a encoder decoder model like a transformer and generate different representations of the same document, and you augment your data. So yes, text augmentation, one of the ways to handle the class imbalance.
Great, thank you. The next question from Ramanpreet. We also do feature selection and feature importance. Is it helpful in NLP task too? So I guess this is coming more from a traditional machine learning piece. Because if we have many features, say 20, many combinations are possible and we cannot try all combinations to see what works. So what is your suggested approach?
Totally agree. So if you remember in the recommendation system, I actually did some feature selection, by the way, a rudimentary approach where I set the min df to 2, which means remove all the words which are occurring in only one movie, which means they are not really useful if you think across all the 4,800 movies. If it's occurring in only one movie, then it's not really useful. So yes, feature selection definitely an important part of the overall pipeline, even for NLP. And you can use traditional methods like frequency cutoffs, or you can use other methods like embedded methods, statistical methods like chi-square, or you can look at the feature importances from tree-based models and also do some feature selection. So yes, they can definitely help for combating overfitting. And if you remember in the use case I talked about, you can use even dimension reduction for that matter, but that can lead you to get non-interpretable features. So you would have to make that trade-off between selection versus dimension reduction. But yes, effective ways to combat overfitting.
Another question, as most of the real world data is unclean, where there might be errors like grammatical mistakes, spelling mistakes, etc., and this might affect the POS tagging, how would you deal with that?
So that is where that optional step, if you remember, where before the POS tagging or before the lemmatization for that matter, you would need to do the grammar correction and the spelling correction. But remember, that is a very expensive process because you need to go through every word sequences of words and correct it. Spelling correction, one of the most simple ways is to use a Levenstein distance and edit distance based method. The more complex methods which have come out recently are using, again, a sequence to sequence model where it has already been pre-trained on a lot of wrong data and right data so that it can translate that wrong data into the right sequence. So that is where these transformer models or the sequence to sequence models can also be used. But yes, you need to do that before you go into the POS tagging and the lemmatization, and that can be expensive sometimes. So yeah.
Okay. Nikhil Bajaj says, using embeddings will always be an edge over TF-IDF, or do you think there are times when TF-IDF is better?
Yes, very good question. So I think if you are working with problems where it is more keyword based, embeddings may not be as useful and TF-IDF can outperform. And we have seen that in many cases. So when you are working with, let's say, a classification problem, which doesn't really care about sequences of words or context for that matter, it is more like, okay, if word A, B, and C are occurring, basically the class is, let's say, class 1. And if word X and Y are occurring, let's say the class is 2. So that is where the keyword-based approach or the count-based approach, TF-IDF, may very easily outperform an embedding system or an embedding model, and especially if you have less data, because in less data, embeddings will not be as useful. So yes, there are many cases when TF-IDF can outperform. That's why you start off with a simple method always. As you know, Occam's razor, simplest approaches can be the best approaches, and then you dive into the more complex approaches.
Right. When you say, embeddings are not useful when you have smaller data, that's when you're generating embeddings yourself, right? Otherwise, transfer learning,
transfer learning can be useful sometimes.
But then
but if your domain,
vocabulary.
Yeah, absolutely. Yeah.
Right.
Yeah.
Right. And so, I mean, a lot of people have been talking about using, embeddings for character engrams rather than words. In your experience, do they get around this problem at all, or is there still a lot to be achieved?
To an extent. So I wasn't able to cover this due to the interest of time, but yes, like fast text model and so on, they will use these character engrams where you basically every word is represented as an average of all the character n-gram embeddings. So they do handle this out of vocabulary aspects and the rarer words representation. So sometimes a fast text model based classifier can be a very effective classifier. So definitely it does handle it, and we have seen some examples. But in our case, again, it didn't output from the TF-IDF, but again, that was for our data. Not that that will always happen, but I do agree with you what you said, where the character n-grams definitely tries to tackle this problem and does it quite well, let's say, versus a word based model like word2vec. So yeah.
And BERT, of course, uses the mixture of the two, right? So it kind
Yes, yes, absolutely. Where BERT uses like a word piece tokenizer, so it will basically break the unknown or rarer words into the subwords. So absolutely, it uses a
right.
combination.
Okay. Another question: what gaps have you identified from your experience in libraries like NLTK and Spacey? Also, what features or improvements would you like to see in these libraries?
So NLTK is easy to say. It's more of a legacy-based library. So if you want to use the latest and the best things, like let's say you want a one-liner for lemmatization, it is not there. You need to code it, if you remember, like I did step by step. If you want to use embeddings, you will not get that. If you want to use different languages, you need to use INLTK, which thanks to some really nice folks, they have done it. Now, for Spacey, I would say it is much better, and they are continuously adding new features to the library. So earlier it used to be slightly limited, but now you have different types of language models for English and non-English. You have different types of embeddings available, and they are even adding like transformer-based aspects to it over time. So I would say for Spacey, it has most of the things needed. The gaps would be basically it doesn't have like an end-to-end system where obviously it doesn't have something where you can just plug in your data and it'll give you the output. So you would still need to like get bits and pieces of it and tie it together and build your own pipeline. So I guess those are the things which are missing. Now, Hugging Face's Transformers is trying to bridge that gap where they are having this pipeline framework where you select a type of problem you want to solve, like let's say sentiment analysis. You can of course fine tune the model, which is slightly more complex, but you can use a model right out of the box and you can pass your data and it'll do the right task for you. So that is where those are the things which I think continuously need to keep getting added in these libraries to give us what we really need.
Great, thank you. I'll put a moratorium on questions now. There are three more, and I'm not taking any more.
Sure, sure.
Unsupervised method of finding out whether a sentence is grammatically correct or not.
Unsupervised method, I don't think I have used, to be honest. So far, what I've seen is mostly, well, I mean, if you consider a transformer model, what it does is it uses unsupervised approaches known as the language modeling, where it tries to figure out the language model of generating every word based on the previous words. And it basically tries to understand which words are related to which words and so on. But that is where you need to fine tune it on, again, sequences of input data of incorrect grammar versus the correct grammar. And that is where it becomes supervised. So that is the most effective method I have seen. Unsupervised method for grammar, I don't think I have seen, to be honest. Something could be done maybe with parts of speech tagging, in my opinion, but that would again be very custom and would involve a lot of rules. Spelling, I know you can use edit distance directly and do, but grammar is very contextual and sequence based. So right now, sequence to sequence is what I've seen, which is the most effective.
Great, thank you. And the next question is, if the comments are in English and native language, so if it's English, for example, how do we solve that problem? How do we deal with it?
Yeah, very tough problem. I definitely haven't dealt with it, but there is something, I forget what the term is, but what they try to do is, again, you need data basically. So they try to convert the English form into an English form, basically. So that is where, again, the thing which comes to my mind, at least what I've seen typically, is like sometimes we may talk in a different language, let's say, like Hindi, but we type it in English. So what someone has tried to do, I forget the exact term for this, but they have a pipeline here where they first convert the English representation into a Hindi representation, let's say. and then they do a language translation from Hindi finally to English. So basically a combination of two sequence to sequence models. Again, you need data for this, to be honest, where the first model will translate from the Hindi representation of the English representation to, let's say, a Hindi representation, and then you translate the Hindi to English using a language translation. But that is where, if it's English, becomes tougher. But without data, I don't think it is possible. So yeah.
Of course, what adds more complexity to you, that is the fact that you don't even know what the other language is, right? Typically. So in the transliteration, you don't know whether it's Hindi or it's Tamil or Bengali for that matter. So
Totally. And the performance also wasn't that great. So yeah.
yeah. And the last question, altering the class weights in case of imbalanced data does improve the accuracy on validation set, but does it really help in the case of improving performance on real world unseen text data?
So that is where it's all about distributions. If the distribution of your feature space is very similar in your training, validation, or cross-validation versus test over time, it will definitely improve. But things will change, obviously, over time. That is where the model retraining comes into perspective. But yes, class weights do help. It has helped us in the past. But the model drift is something to keep in mind, where your performance will kind of decrease over time. That is where you need to continuously retrain and pass the right class weights also. But it does help. But again, not like forever. You would need to update your models.
Yeah, great. Well, Dipanjan, thank you so much. You now hold the record for the longest webinar. It's obviously
Sure.
shows how interesting your webinar was, and how plugged in everybody was to everything you were telling them. I'm already getting requests on WhatsApp saying, can we get him again sometime to go into some of the other stuff that he skipped over. And so, we'd love to have you back at some point, but thank you again. It's been a pleasure to host you. And
thanks a lot. Yeah, there were some glitches, but hopefully we got through it, and I'm glad people liked it. Yep.
Yeah, no, absolutely. I think, uncertainty is something that we live with and are more aware of now. We always lived with uncertainty, but I think we are more aware of that now. And, internet connectivity issues is part of that uncertainty. So
Absolutely.
thank you very much again. It's a pleasure having you. And like I said, I hope that you will come back to us and do another webinar sometime.
Absolutely. Thanks a lot for having me. Pleasure to be here. Yeah. Thanks a lot, everyone. Yeah.
Thanks. Bye-bye.
Thank you, Dipanjan.